In this lecture, we'll see how to classify pictures of digits 0, 1, 2, all the way to 9 as present in the MNIST dataset using convolutional neural networks. So basically, we have images of digits. Each image has one digit, 0, 1, 2, 3, etc. And we want to develop convolutional neural networks to correctly classify them. The original dataset is also at kaggle.com. So let's start. Step 0, that is the first step, it is to load the dataset. Now, we can also load the dataset from other places, but Keras by default comes with the dataset in the library packaged itself. So we can simply do mnist.loadData module to automatically load the data that we need. So we can import TensorFlow and then do tensorflow.keras.datasets.mnist and load data, which gives us this ordered pair with 4 NumPy variables. The first one is xtrain, second one is ytrain, and x validation and y validation. And the next step is to check the number of images and their dimensions. So now that we have loaded the data, let's see how the data looks like. We want to print the shape of this array, xtrain, and the shape of this array, ytrain. I'm naming it original so that later when we change these image arrays, maybe later normalize them, we can give it a final x or y variable name. So if we run this, what we see is that we have 60,000 images in the training set, each of size 28 by 28, and we have 60,000 values as the labels. So if the image has a 0, then the label will be 0. If the image has a 1, then the label will be 1, and so on. And in the validation set, we have 10,000 images, again, all of the size 28 by 28. The next step is to visualize a random image and its label, say in the training set. So say we want to look at the 0th or the first image. So what I can do is print xtrain original, give me the 0th image, and if I print the whole matrix, it's not going to show up in the correct tabular format. So I'm going to select only a range or a portion of the image such that I can view the entire thing as a table of numbers. So if I run this, you can see that this matrix contains a lot of values. Most of them are 0, but the places where we have high intensities, you can see that there's high intensity over here. So it almost looks like a 5, right? So from the pixel values, we can see that it looks like a 5. Now let's plot this these numbers in the form of a heat map to see whether this picture is actually a 5 or not. So here's the same picture now visualized in a heat map. So clearly you can see that this is actually a 5. All the very high values when made shown using white color, and all the smaller values like 0 shown using black color. With the you can see that the color bar is shown on the right here. So this is the picture having the digit 5 in it. Now let's look at the label of this picture. So let's look at the corresponding ytrain NumPy array and look at the value in the 0th position. So here this one has the number 5, which means that here's the image and the label actually is 5, which makes sense. And in this way, we have all the images. So if I go back and let's say plot 5th image, then what I'm going to get is this number 2. And if I print the corresponding label at the 5th, this is actually 6th position, then the label I have is also 2. So we have it. So we have 60,000 examples like these for training. The next step is to reshape and normalize the input so that we can correctly feed this to a neural network. This is because a 2D CNN model will accept a 4-dimensional data input. The first dimension must be the number of data. In this case, for training, we have 60,000. Height, and width, which we have both as 28 and 28. But what we don't have is the channel of depth. So here we need to add one more channel such that we want to reshape each image of size 28 by 28 into 28 by 28 by 1. So we are not adding any values, but simply reshaping to add one more dimension. Also, the image intensities, as we saw, can have values between 0 and 255. We want these numbers to be 0 and 1, and we will do this by normalizing. So we can do xtrain original dot reshape and reshape to 60,000 by 28 by 28 by 1. Simply add this channel. Similarly, reshape the x validation so that we have this additional channel. And then after that, we want to normalize by dividing by 255. So let's do this. And what we have is a normalized xtrain and xvalid. And let's verify that the normalization works by picking up maybe the first image and the first channel of the last channel. There's only one channel. So let's look at this and make sure that the maximum value is a 1 and the minimum value is a 0. So we can see that looking at the color bar, the maximum value, the pixels, the white pixels have the corresponding value of 1 and the black pixels have corresponding value of 0. The next step, step 4, is to reformat our labels, that is our output values, such that they are one-hot encoded. This is because our network cannot predict continuous values, or like these values like 0, 1, 2, 3, 4. It's not a good idea to have one neuron predict those values. So instead, our network should have 10 output nodes, each predicting the probability that the input image belongs to the class 0, class 1, all the way to class 9. And the way we can do this is simply use the function in Keras called toCategorical, which takes all the labels and converts them to, so each number 1 becomes 10 values, where all will be 0 except for the position where it's supposed to be 1. So before we do any kind of one-hot encoding, our original Y-train original is 60,000 rows or 60,000 columns. Here this is 60,000 rows. And if you look at the first value, it's a 5, right? So in this list of original values or correct labels, we have the first value as 5. Now we can one-hot encode both Y-train and Y-valid. So I can do this. And once we encode, what we see is that this corresponding label 5 has become these 10 numbers, where there's 1 at the 6th position, indicating that this is a 5. Similarly, if I print the label for, let's say, the 6th item, then the correct label is 2. So after the one-hot encoding, if I once again print Y-train 5, I should get a 1 here and everything else should be 0. So let me run this, and it's a 1 here. So overall, what this one-hot encoding basically does is, since we have 10 possible output labels, we simply create, for each output label, we create a vector of length 10, such that only at the position where the corresponding label is true, there's a 1 and everything else is a 0. The next step is to create a neural network, and let's say we want to design a neural network with the following parameters. The first layer has 16 filters or 16 kernels or 16 convolutional neurons, each of size 3 by 3. The third layer, let's say, has 4 filters. Well, actually, the second layer let's say, has 4 filters, once again of size 3 by 3. And the last layer must be 10 neurons, because we are predicting 10 classes, 1 for each of the 10-digit labels. So the first neuron will predict the probability for 0, second neuron will predict the probability for 1, and so on. So here's, so we import sequential and dense and conv2D and flatten. So our first layer is 16 convolutional neurons, each of size 3 by 3. Let's say we choose the activation as ReLU, and the input shape is 28 by 28 by 1. And the next is also a conv2D layer, 4 filters, and we also have ReLU activation. And then after that, we have one dense layer with 10 neurons. And then once again, we have 10 dense layers, so total 2 dense layers. Now, before we actually feed the output of conv2D, since this is a volume and this only accepts a vector, we need to flatten the input before sending from convolution to dense. And then finally, we look at the model parameters by printing model.summary. So let's run this. So what we see is we have 26 by 26 by 16 as the output of the first convolution layer, because we actually have 28 by 28 input. The second convolution layer further reduces the size to 24 by 24 by 4. Flattens this by multiplying 24 by 24 by 4, and we have 2304 inputs going into the next dense layer. And finally, the last dense layer produces the 10 value. So the total parameters this network has is around 24,000. Now, here are a few things that we should note. We could just use dense layers to achieve digit identification without using CNNs at all. But CNNs usually deliver better accuracy and they are fit for the problem. Here, conv2D, as you may know, is a convolutional layer where we specify a number of filters first, how many neurons we want, the filter size, what activation we want, and the input shape in the case of first layer. So the filter, as we discussed before, moves through the image pixel by pixel. That is, it convolves around the input image, picking up values. So 28 by 28 input, when applied, a 3 by 3 filter gives output of 26 by 26. And the last layer has 10 neurons, as we saw here, and each of these neurons predict the probability of the digit being either 0, 1, 2, etc. And out of these 10 neurons, whichever neuron has the highest probability will be the label predicted by the neuron. The next step is to compile the model and train the model. So we can choose any adaptive optimizer. Here I'm going to choose Adam. And since this is a multi-class classification problem, we will choose categorical cross entropy as our loss function and the metric as accuracy. So let's run the model.fit statement with xtrain and ytrain as our training dataset and xvalid and yvalid as the validation dataset. So it looks like each epoch is going to take around 45 seconds. Let me actually stop the training and switch to a GPU runtime so that the training can run faster. So change runtime type, and then I'm going to go to GPU and select the GPU as my new runtime. So now after selecting the GPU runtime, let's see how long the training takes. Now each epoch is actually just a few seconds, so let's wait for this to complete. So epoch 1, the validation accuracy is around 94%, and the training accuracy is 86%. At the end of the 5th epoch, we can see that the validation accuracy is 97% and the training accuracy is also around 97%. So this is pretty good. Now let's assess the learning curve. So I'm going to print, in the next step, assess the learning curve. I'm going to print history parameters, what parameters my history has. So epochs is already there. History also has other parameters. Now in this case, we are looking for accuracy, training accuracy and validation accuracy with respect to epoch. So let's plot this. So what we see is that the training accuracy and validation accuracy both go high and almost maintain the same level after 4 or 5 epochs. Let's actually go back and train further, maybe 5 more epochs. So this will continue the training from where it left off. So our accuracy is now around 97%, 97.6 on the training set. The accuracy on the validation set is also more than 97%. So after the 5th epoch is completed, so the accuracy on the validation set is around 97.6%, slightly higher than what we had earlier. And in the next step, let's evaluate the model on the validation set. So we already did that during training, but let's make sure. For this, I can do model.evaluate and give xValid as my input and provide the correct label so it can calculate the accuracy. So this accuracy comes out to be 97.6%, which is what we had seen earlier. The next step is to check exactly what the model is actually predicting. So basically, we are looking for an example of what the model has predicted so that we can compare the prediction with the true and see what the model is doing. So I'm going to set my print precision of numpy variables to 0.2 so that I don't see a lot of those tailing floating point numbers that make the visualization of numbers difficult. So first I'm going to print the validation data, y-valid, the label of the first validation data, and also going to visualize the corresponding true, the input feature map. So here looks like the input is a 7, so the first item in the validation set is a 7, and the corresponding true label is also a 7 because we have 1 at the place of 7. Now what we want to do is to see exactly what the model is predicting here. To do this, I'm going to do model.predict and take only xValid and predict the model and print what the model has predicted for the first data point. So for the first data point, we see that everything else is a 0, but there's 1 at the digit number 7, right? So this is a good prediction. It thinks that it's nothing else but only 7. Now let me increase the floating point precision to 0.7 and see what it is predicting to see if it is predicting exactly 1 or not. So at position 7, we see that the confidence is 99.99, which is extremely high. But if this wasn't the case, then the model thinks that it's either a 0, 1, 2, 3, or maybe even a 9. But since the confidence for 7 is extremely high, the model is pretty confident that it is actually a 7. Another way to also look at predictions is simply to round the predictions by, say, for example, in the first prediction, we can simply round it and see what we get. So rounding simply takes care of the trailing floating points if we had not set the np.print options. But overall, what we see is that the model predicts various values, and then based on the probability, if it is more than 5, then we consider that as a class. Let's look at another prediction. So say, for example, we look at the prediction for the first item. So here the confidence is 0.99. I'm checking for a case where the confidence may not be as high. Okay, so this one, it's confident that it's 1. Let me check another one. So here it's confident that it's a 0 because the probability here is very high. So let's actually print this to see if it is indeed a 0. So once again, we are printing the same thing, but let's actually visualize this prediction, this xValid number 3, to see what it is, whether it's a 0 or not. So it is actually a 0. So the model is doing pretty well, actually. So now, even though the accuracy is very high, if we wanted to further improve the accuracy, the next step is to see what can we do to improve the accuracy. Of course, we saw that using GPUs, the training time can be decreased, and this way we can train longer and do many other things. We can also increase the number of epochs. We only trained this model for like 10 epochs, but if we trained further, maybe the accuracy on the validation set will further increase. We can also try increasing the number of filters in the first layer and the subsequent layers. We can add more layers to the neural networks, that is the feed-forward neural network portion of the network. We can also increase the number of conv2D layers. And we also have to note that the model is actually already doing very well compared to the baseline accuracy. So what do we mean by baseline accuracy? Since we have 10 classes, if the model predicts everything to be a 0, so all predictions are 0, then still the model would get 10% of the data correctly predicted, right? So even a random predictor can get maybe an accuracy of around 10%. But here we are getting much higher accuracies, like 97%. So the model is doing extremely well compared to the baseline accuracy. But if this were a binary classification problem, then the baseline accuracy could be 50% or 60%. So in that case, if the model wasn't doing slightly higher than the baseline accuracy, then that model has not learned anything significant.